G'day Year 11s. I am going to go through exercises 7, D, E and F with you today. There's actually not a lot of new material here. It's stuff that you already know, so it shouldn't be too bad. I hope many of you are able to follow along today. If you're not, I hope you and your families are safe and that you're back in your home soon. Alright, we'll get on with the maths, but look after yourselves. There's plenty of time to catch up on this and you can ask plenty of questions later. Once everything's returned to whatever normal is. Alright, we're looking at piecewise defined functions. We actually looked at one of these the other day when I was talking about when we were looking at domain and range. We were looking at, like the, I think I described it as a car park or something like that, where it has different fees depending on how long you stay in the car park. The example we were looking at, I think it was from 7C, where we were looking at domain and range. There were two closed-in circles there. And that meant that that was not a function. So you've seen a piecewise defined function or a hybrid function. What it is it's a function where there are different rules for different values of x. And you can see in the example here, we've got one rule, negative x take 1, for all x values less than 0. We've got a second rule, 2x minus 1, for all values between 0 and 1. And then a third rule, half x plus a half for x values greater than 1. And so to sketch that, all you have to really do is sketch a straight line and just stop it in the appropriate areas. So for the first bit, negative x minus 1, I've got a gradient of negative 1 and a y-intercept of negative 1. So I know it's going to go all the way down to negative 1. At the moment, I'll have an open circle there because it's not equal to 0 at that point. It's only less than 0. And then negative x, that's got a gradient of negative 1. So if I could draw more accurately, you would see that that's got a gradient of negative 1. And that would be the appropriate thing. That continues off in that direction. It's a straight line, so I'm happy to put an arrow on the end of it. The second bit, for values between 0 and negative 1, we've got to follow the rule 2x minus 1. The easiest way to do this, remember we need 2 points. I substitute in x equals 0, and I'm going to get 2x minus 1. Well, that's 2 times 0 is 0, minus 1 is negative 1. So it is actually going to join up there. So I can make that a closed-in circle now. And I've got a gradient of 2, which means I'm going to go up 2 for every one that I go across. So I'm pretty sure it's going to go through the point 1 and 1. You could just as easily substitute in the value 1 and you go 2 times 1 is 2, minus 1 is 1. So I know that it's going to follow that rule up to there. This intercept is going to be at 1/2. Finally, a half x plus a half for x values greater than 1. Well, if I let x equal 1, I'll have 1/2 plus 1/2 is 1. So it would have had an open circle there, but it's already closed in from the previous function, so it's going to be continuous. And now I've got a gradient of a half, so I'm going to go up 1 for every 2 that I go across. So now I know I'm going to go through when it behaves for me. There you go. I'm not allowed to scribble, obviously. Going through the point 3,2 because that's up 1 and across 2, so I've got a gradient of a half. And it's going to continue in that fashion. We've sketched it. You already had seen that. Over here on the left, they've talked about why it's true, but hopefully that's pretty easy. The range of f, if we're looking at the range of this function, this is going to continue, the right-hand portion here is going to continue going up with a gradient of a half. The left-hand portion is continuing going down from left to right, or if I'm continuing back towards the negative numbers, it's going to get bigger and bigger. As x becomes more negative, y is going to become more and more positive. So in actual fact, the graph will continue rising forever, but will never get lower than negative 1. So my range for part B is just going to be the set of y values such that y is greater than or equal to 1. You could have, if you wanted to be really good, added in y is a real number. Y is an element of the set of real numbers. Y is greater than or equal to negative 1. That would have been lovely as well. Just as happy for you to go negative 1, comma, infinity here as well. It's allowed to equal negative 1 or be anything bigger than negative 1. You can see that's the way they wrote it in the book. Even just y greater than or equal to negative 1 would be acceptable in an exam though. That's all there is. That's the sum of all of their examples for this. They're just talking about the fact that you have different rules for different parts of the function, so you just sketch each bit separately. Nothing overly complicated there. If we jump ahead to 7e, applying function notation, this is just saying everything you've done in the past where you said y equals or v equals or a equals or anything like that, we can use function notation. Here they've got the example, the volume of a sphere of radius r is determined by the function. The volume in terms of r is 4/3 pi r cubed. So rather than just saying v equals 4/3 pi r cubed, they're now saying v of r equals 4/3 pi r cubed. State the practical domain. What values make sense for a radius? R greater than 0, I think would make sense for me. Do I have a sphere if r is negative? No, that's pretty hard to picture. Do I have a sphere when r is 0? I could probably be happy with that, but I think many people would be upset by that. So we're going to go with a sphere. For it to exist, it must have a radius. So the radius has to be greater than 0. So there's the practical domain. And find v of 5. V of 5 is pretty easy. V of 5 is going to be 4/3 pi times 5 cubed. 5 to the power of 3 is 125 by 4 is 500. 500 pi over 3 would be the volume. And there you go. They didn't give us units there, so we can't say what it is. We could say cubic units if we want to be aware of what we're doing. And it's not bad to exercise your brain and make sure you're aware of what you're doing there. I wonder in the book what they did for 7, whether they included 0 or not for that question. I'm just thinking out loud here. Let's go and have a look at their example. No, they said can't include 0, and I think that's reasonable from my perspective as well. So for once, I agree with the book. That's good. They make a point here about v that being the dependent variable because it depends on the independent variable. That's usually the way it works with our x values being independent and our y values, the vertical axis, depending on the x values. Not always the case, but generally the case. What other questions have we got here? A function has a rule f of x equals ax plus b where a and b are constants. F of 1 equals 7, f of 5 equals 19. Wow, this is just a fancy way of saying solve the simultaneous equations. Let's see, f of 1 equals 7. So I can say f of x, I'm going to call that 7, is equal to a times 1 plus b, which of course is just going to simplify to 7 equals a plus b. There's my first equation. And what else do they give me? When x is 5, the function is 19. So 19 equals 7a plus b. That's my second equation. Find the values of a and b and hence sketch the graph. So it's pretty easy from here, isn't it? We're just going to use simultaneous equations. I'm going to go equation 2 minus equation 1. 19 minus 7 is 12. 7a minus a is 6a, and b minus b, they disappeared. I love elimination because it gets me to my answer quickly. I've got a equals 2. I'm going to let a equal 2 in equation 1. Therefore, 7 is going to equal 2 plus a. Oh, sorry, 2 plus b. I'll let a equal 2. Subtracting 2, I've got 5 equals b. Therefore, the equation is f of x equals 2x plus 5. And we can go ahead and sketch that very easily. Gradient of 2, y-intercept of 5. Right through the 5 where I put it. Look at that. You can find your x-intercept, let y equal 0, subtract 5, divide by 2. That's at negative 5 over 2. I should make that 5 look like it's in a better place. Label my equation. And we're done. Last one there, same thing, a quadratic function. This time it told me f of 4 equals f of negative 2 equals 0. This is important because here I've been given two intercepts. I can see it equals 0. If I'm given the intercepts, I'm going to use my intercept form. x minus the first x-intercept, x minus the second x-intercept. So I want to use that form. So now I've got f of x must be something, if 4 is an intercept and negative 2 is an intercept, I can write x minus 4, and x minus negative 2, of course, becomes x plus 2. Now I have to figure out what that a value is, but they've given me another bit of information. They've given me a y-intercept here. When x equals 0, y equals 16. Substitute in 0, 16 to solve for a. So 16 is going to be a. When I substitute in 0 in the first bracket, I have negative 4. When I substitute 0 into the second bracket, I'm going to have 2. 16 equals negative 8a, divided by negative 8. Negative 2 equals a. And I've got my equation. F of x equals negative 2, x take 4, x plus 2. And we are done. Wow, 2 exercises down, 1 to go, and we're cruising. This is not too difficult. There's a few questions to practice for you, which will be good, give you something to do, but it's not going to be too bad at all. Finally, functions and modelling exercises. We're just showing we can use maths to model functions. This one's interesting because of this little note they make down here. So let's just read the question first. A book club has a membership fee of $60 and each book purchased is $10. Construct a cost function that can be used to determine the cost of different numbers of books and then sketch its graph. They've told us, they've defined some values. They've let C of n be the function, the cost in dollars where n books are purchased. So C of n equals 60, the fixed amount, plus $10 per book. I think we're all okay with that aspect of it. The interesting thing here is that we've got the set of integers, natural numbers here. They've said natural numbers or 0. So the set of non-negative integers. Because we're using integer values, we shouldn't be joining these individual points up because it doesn't make sense to have a value where the number of books is 4.3 or 4.6 or something like that. It only makes sense to have a whole number of books. So strictly speaking, when we sketch these graphs, we should have discrete points, discrete values listed. This becomes important when you're doing an IA. You need to think carefully, and this is not just for maths, but in your sciences as well, or anything else, geography. Whenever you're sketching something, think about whether your data is discrete or not. If it is discrete, you should be showing them as discrete points. You could choose to add in a trend line, but the data itself is discrete points. This data is only satisfied, this data set's only satisfied by values of n that are elements of z plus or 0. Now they've said the natural numbers or 0, which is the same thing. Once you've got it there, though, it's pretty easy to see what it looks like. So I wanted to mention that because that could be important in assignments coming up one day in maths or in one of your other subjects. Finally, another good one here, we have a piecewise function again. Sketch a graph of the cost function, giving its domain and range and the rules that define it. This time, it's not a car park, it is the cost of postage. N, well, little n. No, M for mass. Sorry about the squiggly line there. This new computer doesn't let me draw quite as neatly as my previous one. This is going to be my mass. No, my mass is in the other one. This is going to be my cost in dollars. This is my mass in grams. And so up to 50 grams. So from 0 to 50, we can't have a parcel with negative grams. So we've got to get to 500. I should think about this more carefully. 100. 200, 300, 400. Let's assume that I didn't change my scale and I kept that all nice and even. You, of course, would be using a ruler, so it's not a problem. My cost, my maximum cost is $3. Let's go $1, $2, $3. Now we're ready to sketch in the function. So up to 50 grams, the cost is 70 cents. So I'm going to have 0.7 here. Up to 50 grams, it's going to cost me 70 cents. Now you can argue whether something could be as light as 0 grams or not. I'm happy for you to have an open circle there. If you don't post a parcel, it doesn't get sent. If you coloured it in, I wouldn't be detracting marks because maybe it's so light that it doesn't register on your scales that you have set up. It would still, if you were going to mail it, cost you 70 cents. So I'm not too concerned either way. Over 50 and up to 100 is $1.15. So I'm going to estimate $1.15 there. Over 100, so not including 100, and up to 100 is at $1.15, so $1.15. Between 100, over 100, sorry, and up to 250, it's $1.70. So here's 1.7, over 100, and up to 250. We're getting a bit further along now. There it is. And $3 is for over 250 up to 500. Open circle and a closed-in circle. And there's your piecewise defined function. Giving its domain. Domain. What values can I input it? This is going to be mass, M, so I'm going to have M. And I could say it's greater than 0 and less than or equal to 500. And if I measured that in grams, that would seem reasonable. Again, if you had greater than or equal to 0, I don't really mind. But your domain makes sense. It's defined, and it could be any value in that range, in that range of values for M, 0 up to 500 grams. The actual range of the function is quite limited. It's 70 cents, $1.15, $1.70, or $3. Can make a note there that those amounts are in dollars if I want to. There are only 4 possible numbers that I can get out of this function. Lots that I can put in, an infinite number of measurements between 0 and 500 grams, but only the 4 possible output values. Still a function because at no point does a vertical line ever cross more than one part of the graph of the function, so that's what it would look like. There's another piecewise defined function. Last question. Householder has 6 laying hens and wishes to construct a rectangular enclosure to provide a maximum area. So we're going to have to maximize a rectangular area. So I might make a note. The area of a rectangle equals the length by the width. I'm sure you're all going with that. They're going to do this using 12 meters in length of fencing wire. So assume it's quite tall fencing wire and maybe it's chicken wire or cyclone wire or something the birds can't escape from, the laying hens can't escape from. So my total perimeter, which is going to be made up of a length and a width and a length and a width. I don't mind if you write 2L plus 2W or 2 bracket L plus W. It doesn't bother me. That's going to equal 12. I can simplify this, get the length equal, 6 is equal to the length plus the width. When we're dealing with all of these questions, the aim is to get one variable. See, we've got 2 variables, length and width and length and width. We want to get down to one variable. So I'm going to let width equal 6 minus the length. Just subtracted L from each side. And I've got the width is whatever I get when I take away the length from 6. So now I can find the area in terms of the length. It's going to be the length multiplied by 6 minus the length. Oh, okay, I've got my area in terms of length. That's what it said. Construct a function that will give the area of the enclosure in terms of its length. And by sketching a graph, find the maximum area that could be fenced. You could find it without sketching, but let's sketch it anyway. It's already in intercept form. Area, length. I don't really need those bottom sections because I'm only going to be increasing. My area, we've got meters, so this is going to be in meters squared or square meters. And the length is going to be in meters. Here I go. I've got a parabola. This is, if you want to look at the expanded form, 6L take L squared. A sad face parabola. The coefficient of L squared is negative. But I can see that it's in factorized form. One intercept is going to be at 0. The other intercept is going to be at 6. It's a parabola from a quadratic equation, so a nice symmetrical equation. Where is the maximum going to occur? Well, halfway between 0 and 6 is 3, so I know the x-coordinate of my maximum is 3. And if I substitute in 3 into the equation here, I'm going to have 3 times 3 is 9. And so the maximum area is 9 square metres. 9 square metres when L equals W equals 3. Of course, once you've got that equation, you could have just found the maximum by using your coordinates of the turning point negative b on 2a and 4a squared. 4ac minus b squared all over 4a. Negative b on 2a. Remember, they are the coordinates of the turning point of any parabola. So you could use that as well. That's it. 3 exercises. Plenty of work to keep you busy today and possibly into tomorrow. Do we have maths tomorrow? Tomorrow is... yeah, we have maths in period 3. Now, I know that school's been cancelled, and if you have better things to do, please go and do those better things. Please look after yourselves, your families, your pets, your friends, everyone. But if you are bored and looking for stuff to do, break open your maths textbook and have a go at those 3 exercises. That should keep you busy. Good luck, everyone. We will see you when we're all back at school, hopefully very soon. Bye for now.